welcome to the lecture of this finite volume method. So, where we have stopped, actually we will start from there. So, what we are doing is the discretization process of the system, and when we are doing the discretization process, there are few steps, and there are steps like 1, 2, 3, 4, and like first we define a domain and then the domain to physical modeling. So, we have already discussed about the domain modeling. We have, this is our actual domain. If you recall from our last lecture, actually this is the heat base, and you have a microprocessor here which is essentially behave like an heat source, and there is a heat sink here. So, this particular patch is going to take care of the heat, and the outer periphery of the base is insulated. So, that means there is no heat flux. So, this is our physical domain, and the physical modeling, that means for this particular case the governing equation that we are solving is our steady state heat transfer equation with some heat source. So, this is what we are solving. So, first thing, we have a physical problem in hand like this kind of a heat base, where heat source, heat sink is there, isolated base plate, and the physical equation or the governing equation that actually govern this particular problem is the steady state heat conduction process, and which will get us the temperature distribution. Essentially, we are interested in temperature distribution in this particular heat base. So, which will lead to finally the design of this particular system. So, we have done domain modeling, we have done the physical modeling through the equations. Now, we have come to the stage where actually the equation needs to be discretized. So, we are in the process of equation discretizations, and then finally, once we assemble the process, because equation discretization will lead to the linear system. So, this is what we are supposed to do. So, that means this is where we apply our, and this particular step we apply our numerical technique. So, which could be of finite difference, which could be of finite volume, which could be of finite element. So, for this particular scenario, since we are interested in finite volume method, so we are applying our finite volume discretizations, and from the equation, that means this is the particular equation that we are interested, because this system is governed by this particular heat transfer equation, steady state heat transfer equation with a heat source. So, these equations, once we do the discretization, it gets the linear system. That means essentially Ax equals to B. Then finally, once we solve this linear system, the solution will give me the temperature distribution inside this particular domain. So, the first step to get the equation discretization, that we need to divide this particular domain. This is our physical domain. This domain we need to divide into proper control volume or the finite control element. To do that, so this is one of the way one can discretize. This is the structured grid. So, from your last lecture, if you will recall, so this is what one can do. So, essentially the complete domain is divided or subdivided into multiple small finite elements. So, each of these calls the finite elements or control volume. So, small control volume which will finally lead to this particular heat base, and the patch 1, that means along that surface, the outer boundary of this heat base, along this particular boundary, this boundary, this boundary, we have a boundary condition, and that boundary condition is essentially the no heat flux boundary condition. As soon as we say it is an insulated system, then we do not have any heat flux boundary condition. And if you look at the boundary condition thing, this heat flux boundary condition is a boundary condition of Neumann type, and these patches like patch 2, this is the heat sink. So, heat sink means there will be a temperature. So, it will have a distillate type boundary condition or constant temperature boundary condition. So, the boundary condition that we have discussed so far, they all, at least couple of them, you can see the direct application in this particular problem. One is the distillate kind of boundary condition, which is applicable to patch 2 and patch 3. patch 3 is the heat source. So, that will have a high temperature. So, this is the source. So, it could have a high temperature, or patch 2 which is always the heat sink. So, that means there will be a low temperature. One way other possible is that since the patch 3 which is the microprocessor, it could be the heat source and it could give us the heat generation also. Instead of temperature, the source term could be the heat generation in this patch. So, either thing is possible, but essentially that is why the whole system of equation that we are solving here is the steady state heat conduction equation with the heat source. So, this particular patch will lead to the heat source term, and then the equation using our FBM method we will get a linear system. Once we solve the linear system, we will get the temperature distribution. So, this is the problem definition that we have been discussing, and now how we proceed with that particular problem. And if you see this particular domain, we have assigned 1 to 25 elements or the small sub elements or control volume, these are all finite control volumes. So, what is important here to note that each of these interior points, these are all interior points or points, you can say these are the interior vertices, but this control volume or the finite control volumes which are the interior elements, they are connected with neighboring elements. So, what is very important is that keep a track of this neighboring element. So, let us say if you consider this element, then the neighboring element would be 4, number 8, 10, 15. So, this neighboring element will have an impact. As we move on, if you see that particularly this numbering, then this we consider the element number 9, then element number 9 is surrounded with other 5 neighboring elements like 3, 4, 5, 10, 16, 15, 14, 8. Now, if you just consider only this particular element and you take it here, so from there if you take that particular element, this is what we have been doing, let us say mark it as a C, this particular element, element number 9 in global domain. So, now if you see the importance of this particular element structure here, that once you mark the complete domain or the computational domain, that with a global element number, now once you try to discretize the equation, you come down to the system where it is a local, but that connectivity must be maintained, and this is called, if you consider only one particular element like element number 9, around that this particular called the discretization stencil. Stencil means the particular finite element or the small element what is surrounded with a different connecting elements, like for this particular case the neighboring elements are 3, 4, 5, 10, 16, 15, 14, 8. So, that is how it is surrounded. If you look at the vertex connectivity, 9 and 5 is connected with this particular vertex, 4 and 9 is connected with also this common vertex and this particular one, then 8 and 9 having this and this, 9 and 15 are having this and this, 9 and 10 having this and this. So, they are also connected with these 4 corners. So, since we are looking at a 2-dimensional structure, so it is only a 4 corner, and if you, since also you are in 2D domain, the element number 9, if you look at this particular picture, they are connected with 4 faces, the phase 1, phase 2, phase 3 and phase 4. Now, if you same thing, if you move to the 3-dimensional domain, there will be 6 faces, because then you will get an hexahedral element. Right now these are quadrilateral element, and quadrilateral element you got only 4 faces. Now, this is the element 9, so I mark it as a C, and now upstream of that there is F1, north of that F2, downstream of it F3, or you can say the west side of it. So, this is how we are following the convention: east, north, west, south, and this is F4, and the element C and node 4 or the element F4, they are sharing the phase F4. Similarly, C and F1 sharing a phase F1, C and F2 sharing phase F2, so and C and F3 sharing a phase F3. So, essentially a particular 2-dimensional element sharing phases like that. So, it is sharing 4 phases. So, what is the equation that we are solving? Let us say we write the equation for the element C. So, equation we are solving the integration of these equations with So, this is how you discretize over this control volume. Once we write for one particular element, you can actually continue doing that and get an equation or the complete equation, because your complete equation would be having Ax equals to b, and this matrix, what does it contain? That is what we are trying to achieve. This matrix will contain all the coefficients coming from all these elements starting from 1 to 25. But if you look at for a particular element, now in the programming actually you transform the complete thing to a global matrix. Now what we have done so far is, this is the equation. If you just look at it, the equation is in this particular form. So once you get this particular form, this is the integration over the surfaces. So the integration over surfaces has been done. So you get a summation of this, and f got all 4 surfaces. So f got f1, f2, f3, f4. So all these things are getting over the loop, and if you simplify from this step to this step, if you simplify, so if you write down f1 into sf1, so that means the S is the area of face 1. So sf1 is nothing but the area of face f1. Similarly, sf2 would be area of face f2. sf3 would be area of face f3. Similarly, sf4, that is the area of face f4. Okay. So or you can say basically this is instead of area, you can say that this surface vector, rather you say it is a surface vector. So that is better. So you call it a surface vector for each of these faces, because f1, f2, these are the surface vector. So it is a surface vector of face f1, okay, and that goes outward from element C. Okay. Similarly, this is surface vector of face f2, this is surface vector of face f3, this is surface vector of face f4. And if you look at that in this particular picture, so if you look at it, now this is how it has been done. This is element C, it is in the cell center. So that blue dot here actually define your cell center, and this is your f1 which is at the east face or east side of the element C, this is your north side of the element C, this is your west side of the element C, this is your south. For particularly for this particular case, we have defined this is f1, this one f2, this one f3, this one f4, and if you look at the vector, this connecting C and E, the connected with a surface f1, and the sf1 is the normal vector. Similarly, f2 which is connected between f2 and C, this one goes to the sf2 is the normal vector. When you look at C and f3, the connecting normal vector is sf3, and they are all pointed outward. Okay. And how you define then sf1 as we have defined. So now this particular element is divided in uniform size. So C element in the x direction, this is your coordinate direction x and y. So this the size of element C or the width of element C, this has delta x and delta y. So this is delta x and this is delta y. Now the distance between center of C and f2, that is also delta y, because it is assumed that this mark here and mark here, they are all at cell center. So once you assume they are cell center and the grid distribution, that means the delta x is uniform and delta y is also uniform, but that does not mean delta x has to be delta y. This is not true. It is what is that whatever domain length you have that is uniform. Let us say you have Lx, you divide by n number of points, then you get delta x. Similarly, Ly divided by ny number of points, you get delta y. So, this is what we mean by delta x uniform. So, this would be also delta x if I consider. So, that is what we mean to say. So, this is also delta y. So, what does that do? The distance between two cell center is also delta y, distance between two cells in the downward is also delta y. So, if I write the surface vector SF1, this is pointed towards the positive direction of x. That is why this delta F1 into I. So, it gives you the direction of this is, if you, it is a two dimensional domain. Since it is a two dimensional domain, the other direction or the span wise directions you have a unit length. So, if that is the case, this is the length multiply with the unit length is the area and the direction vector. So, it is a area normal vector. So, it gives you delta YF1. Similarly, delta XF1 is the distance between this and this. So, you get XF1 minus XC. So, essentially delta XF1 for this particular case, as we assume they are uniform distance, even then if you write delta XF1 and delta XF2, they would be actually same, they are all delta x. But for the sake of discretizing the equations, we continue with this particular format, so that you get an idea, not necessarily they have to be uniform. Even then if you have a non-uniform delta x, you can write this formulation. What it requires is that when I go by this particular direction between C and F1, I need the distance between this cell center to this cell center, and that is what I mean by delta x F1, which is more generic in writing, but essentially it boils down to this particular case would be the same. Similarly, delta TF1, it is a derivative of delta t at phase 1 and 2 component, and derivative of delta t at phase 1 y component with j. So, that is what you write the delta TF1. So, what even then if you look at it, so if you see the other component, the xc and all these, they are the centroid of the C element. So, you can write down the other component and let us say xc, xc is the centroid of element C, right. X F1 is the centroid of element F1, okay. Delta y F1, as I have written here, area of phase F1. So, similarly you get all other component like F1, F2, F3 and F4. So, now if I expand this particular term, now I have delta T F1 dot SF1, that is what we have got here. So, if you look at this particular equation, this is finally we have got, and it has all the component of all the phases. So, if you look at this component, so essentially this is delta t by del x by del t I plus del t by del y j dot you have delta y F1 I. So, which will get you back, so now it is a dot product which will get you back del t by del x at phase F1 into y F1, okay. So, similarly you can get, now the important thing is that you can get the other like delta t F2 into S F2. So, you can get all this other information. Now, the point comes if you move ahead along this direction. So far we know how to get these dot products. So, if I get these dot products and put those equations back in the algebraic equations where all the integration is done over the faces, I can get all the component. Now, still one component which is missing that needs to be evaluated is this particular component, and which is true for all other phases like F1, F2, F3, F4. Now, we need to find out now how do you do that. So, essentially it is a first derivative of temperature at phase F1 Okay. So, here when you come down, even so what we are trying to do through the finite volume discretizations, anyway we will have more detailed discussions and all these, but that is get you the idea what we get to the linear system or how we get to the linear system. Now, if you look at this particular derivative, now we have to approximate, and this is where the derivative approximation comes into the picture, and towards the end of this lecture we will also discuss how we find them, and the derivative calculation is exactly similar how you do in the finite difference method. So, that using the Taylor series expansion. So, the detailed discussion will follow up later, but now for the time being you say that this is done with a simple arithmetic, that the difference between the two cell center, this is my cell center, this is element C, this is element F1. So, the temperature difference between these two by the delta x F1. Okay. So, this particular equation now boils down to delta T F1 dot S F1 becomes now T F1 minus T C delta x F1 delta y F1. Now, if you look at this particular expression here, this is very interesting. You started with a equation, partial difference equation, you integrated over the finite volumes, and then finally what you got, at least one component what you see is only the information of some algebraic expression, or the values which you require is some sort of a floating point data or the double precision data or the so, these all these informations are only scalar quantity, there is no vector involved, no integration involved. So, it essentially brings down to the algebraic system with all these component. Now, if you put them together, so if I have to look at this term k delta t at f1 dot s f1, this will become a f1 t f1 minus t c. What is a f1? So, this is my term, a f1 is where a f1 would be nothing but minus kappa delta y f1 by delta x f1. Okay. So, this is for phase 1. Similarly, now particularly this element, if you see, this is your element C. So, this side, this is your f1, f2, f3, f4. Similarly, you can find all other component like this. So, if I have to put them together, I will put the coefficients only, minus kappa delta x f2 by delta y f2, a f3 would be minus kappa delta y f3 by delta x f3. Then we have a f4 which is minus kappa delta x f4 divided by delta y f4. Okay. Now, when you substitute everything in that particular algebraic equations, the equation was like this, summation over phases, that means around that element C, equation was k delta t f dot sf equals to summation of now f around these faces af into t f minus t c. So, if you write down them together, they will get a f1 plus a f2 plus a f3 plus a f4 into t c plus a f1 t f1 plus a f2 t f2 a f3 t f3 plus a f4 t f4. So, it will, and that equals to my q dot c b c. So, that now this particular system is nothing but a linear system. So, if you see how a PD equation through this numerical approximation you get back to a linear system like this, and this now nothing but a algebraic system, but only thing is that this is for the only one element. What you have to do, you have to integrate over all the elements. So, if you write in a compact form, if I write more compact form of the same for element C, what I can write is AC TC plus summation of capital N AF TF equals to BC, and in this AC is nothing but minus AF1 plus AF2 plus AF3 plus AF4, okay, and BC is Q dot C BC. Okay. Now, if you see, they have been all put together, and the elements which were there around that element, this was my element C, or essentially element 9 in a global system. This was my F1, but in a global system it was 10. This was my F2, in global system it was 4. This was my F3, in global system it was 8, and this was my F4, in global system it was 15. So, neighboring element was for 9 was 10, 4, 8, 15. So, this is where once you bring them together into the global system or the global matrix, they will be, now this is where element C now connected with 10, 4 in the F2, 8. So, this numbering 4, 8, 15, 10, they are actually the global numbering, and these global numbering once put them together, so you see the matrix like that. So, what I am looking here, so this was my heat base or the problem that I was solving, or the physical problem that I was solving, and this is the element that we have considered. Now, if you look at some row of this particular, this is your A, this is your X, this is your B, and B will contain all these starting from B1 to Bn. For element C, what we have C, the BC is essentially Q dot C by into Vc. So, if you transform them to global system, that will contain here somewhere, which is nothing but B9, which is Q9 B9. Like that, I have all the B1, B2, B3, Bn, and this is where it goes from 1 to again 25 in this direction. N is essentially 25 in this. So, each of these component, now since this is 9 and the neighboring elements are all these 4, 8, 10, 15, only those component will be active for this particular row. And what does this system actually tell you? Once you then you go over a loop starting from 1 to 25, if you get the system of equation like this is the system of equation which you write for the all the elements, you assemble them together and you get this global matrix. Okay. Now, once you get this global matrix, then you need to get the solution. So, the step towards that, when you are doing the equation discretization, so your final objective is to get the linear system. Okay. And to linear system, you apply your numerical technique like FBM and you get a linear system. Once you get a linear system like this, now the next step or the final step, getting a solution. Now, what can happen? Typically this matrix what you are getting, it not necessarily has to be very smooth. not necessarily, because once you talk about Navier-Stokes equation, they are not going to be smooth. It could be sometimes sparse, it could be sometimes essentially banded, it depends on the particular PD. So, essentially it will depends on PD that we are solving for. So, in a nutshell, you can think about when you solve the realistic problem with the Navier-Stokes equation, this A is essentially a sparse large system. So, here the example that we have taken is n is 25. Now, when you talk about a big system, so n is 25 by 25. Now, when you talk about large scale problem like problem around automobile, problem around aircraft structure, you think about to represent that physical system what kind of n, or this will be your number of elements that is required to represent that particular system. So, once n become large, solution of this system becomes challenge. So, we will stop here today and we will take from here in the follow up lectures. Thank you.